In my last video, I built this robot and solved the inverse kinematics to get its top plate moving. This was fun, but I want it to be able to do more. So, in this video, I'll be turning it into a mobile robot that can stand up and walk around. The basic idea is that I need to find a pattern of movement for the top plate that causes the arms to hit the ground, lift the base up, and move the bot to a new place. But how can I figure out this movement for the top plate? Well, like with every other problem I can't solve, I'll be turning to AI. Specifically, I'll be making a genetic algorithm to solve the problem for me. As defined by Goldberg in his book on the topic, genetic algorithms are search algorithms based on the mechanics of natural selection and natural genetics. These algorithms start off with an initial population of organisms with random genetics. Each organism is a possible solution to the problem, with its genes representing the characteristics of that solution. The goal of the algorithm is to evolve this initial population into a new population better fit for the problem. To move in this direction, the algorithm first evaluates the fitness of each organism with the fitness function. This function scores each organism based on how well they can solve the problem at hand. Next, some of the higher performing organisms will be selected and become the parents of the upcoming generation. Their offspring receive genes from each parent and occasionally will be given mutations where their genes differ from both parents. We'll also include a small chance that some of the selected parents do not produce offspring and will simply continue on as part of the next generation. The genetic algorithm works by repeating this cycle of evaluating the population, selecting parents, and creating offspring with the occasional mutation. Selection is biased towards higher fitness to give the next generation a better place to start. Producing offspring is done to combine different parts of good solutions to make even better ones. And a mutation is there to add in some new ideas that may not have existed in the selection. After several generations, if it's worked, we'll have a population of solutions that are well fit to our problem. In this example, it seems to have found that thin, blue and green shapes were good solutions to whatever problem the fitness function scoring was based on. So how can we apply this to get the robot walking? I think the best place to start is with the fitness function. We need a way to evaluate how well a solution makes our robot walk. The easiest way I see of doing this is to run the solution and measure how far it's moved after a set amount of time. I can't do all these measurements by hand, so we'll create a simulation that a virtual robot can move around in. I spent some time getting the simulated results to be close to the actual movements of the robot. This simulation will be our fitness function. We can test out a solution in the simulation, and the distance traveled will be its fitness score. Next, we need to figure out what a solution to our problem even looks like. So far, I've only mentioned that a solution will be a pattern of movement for the top plate that makes the whole robot move around. I'd also like potential solutions to be able to take advantage of all 6 degrees of freedom the robot has. And, at least for now, I'd like the solutions to be simple, cyclical movements that can be looped over and over again. This still leaves a lot of possibilities for ways to define a solution, but the one I came up with was to use a combination of sine waves, one for each degree of freedom. These will create repetitive motion in x, y, and z, the translational degrees of freedom, as well as in roll, pitch, and yaw, the rotational ones. To come up with a specific solution, we need to set the parameters for each sine wave. First, we have the amplitude, which controls how far the top plate will move during a cycle. Increasing this value will make larger, faster movements. The period is the parameter that controls how many seconds each cycle lasts. So if we were to set p equal to 2, the pattern would repeat every 2 seconds. The phase shift will move the entire wave forwards or backwards in time. This is difficult to show in the movement of a single sine wave, but has an important effect on how the individual waves will combine together for the overall pattern. The fourth and last parameter is the vertical shift. The vertical shift changes where the motion is centered about. Increasing this value will shift the entire wave up, keeping the same pattern but at a different position. These 4 parameters can be changed for each of the 6 sine waves. This means we'll have 24 total variables, each having their own effect on the movement of the robot. Finding a combination of all these parameters by hand is a difficult task, especially when you remember that we aren't actually concerned with how the top plate is moving, but instead with how the resulting arm movement can make the robot walk. And that's where this algorithm will be useful, in helping search this massive space of potential solutions, where the individual parameters we can change have confusing and convoluted effects on the outcome we care about. Now that we know how the movement will be defined, we can start building the initial population. To do this, each organism will need a set of its own sine waves. We'll get random parameters for each of them, staying within certain limits. Genetic algorithms need a way to encode all the information about a solution. The encoded information is called a genotype, and each organism will have one containing its solution to the problem. The typical way to encode these is in a list of ones and zeros. Sticking with this method, we'll map each parameter to a binary value and add it to the end of the genotype. And as long as we keep track of how and where each parameter is encoded, we'll be able to decode each genotype back into its sine waves. This encoding and decoding may seem overly complicated, but it's needed for using the standard methods of genetic algorithms. And with that, we're almost ready to start the fitness function. We just need to set up the initial population by randomizing some more genotypes. As the simulations begin, we can see that most of the solutions aren't too good. The bases are staying still, and most of the arms aren't hitting the ground. This was expected though, since all of the genes were completely randomized. Once our fitness function, the simulation, has finished, each organism will be given a fitness score. These scores are measured in millimeters traveled and are needed for the selection of parents for the next generation. But before that, let's see the best from the initial population. This one was able to move 3 millimeters, and watching it back shows that one of its arms was able to hit the ground some, moving it a tiny bit to the side. To build the next generation, first, we need to select some parents from this one. There's many ways to make this choice, but we'll go with the simplest, called roulette wheel selection. On a wheel, each organism will be given a section with an area proportional to its fitness score. With this, better solutions have larger wedges and better chances of being selected. We'll spin the wheel, selecting a new parent with each spin. After selection, the next step is crossover. To make this process easier to see, I'll shorten the genotype, but know that everything should be done on the entire sequence. With the selected parents, we'll now decide if they make offspring with crossover or if they continue on as part of the next generation. After spinning the wheel and seeing it land in the larger section, we'll move ahead with crossover. As with selection, there are many ways to create offspring, but again, we'll be using the simplest method, called single-point crossover. This is done by lining the 2 genotypes up and selecting a random cut point between 2 of the genes. Offspring are then made by combining the first half of one parent and the second half of the other. Then by combining the second half of the first parent and the first half of the second. The final step is mutation, and for this we'll set a small probability of occurrence. Once at each gene, we'll spin the wheel, and if mutation is to occur, that gene will be flipped from a 1 to a 0, or a 0 to a 1. This process of selection, crossover, and mutation is then repeated until we have enough genotypes to build the next generation. It's difficult to see small improvements between consecutive generations, so I'll go ahead and skip to the end of the algorithm, where we've evaluated hundreds of generations, building each new population based on the results of the last. Plotting out the average fitness for each population across a few hundred generations, we can watch the evolution into a much more fit population. This final generation is a massive improvement over the initial population, but averaging 14 millimeters traveled in a 10-second simulation isn't too fast, and I think we can do better. Before restarting the algorithm, I decided to remove the genes for the periods of the sine waves, and set a uniform period across all the degrees of freedom for each robot. I did this because in the previous algorithm, the different degrees of freedom weren't syncing their movements up well. Removing them cuts out interesting solutions that may have been found, but I think this is the best method for finding better solutions now. We do have to make a decision about what the value of the period should be though. If we set a specific number for every robot, let's say 2 seconds, we may end up with a situation like this, where larger movements have an advantage because their arms can reach much higher speeds. The solution I came up with was to first assign the same period to each robot. Then, I would test out the solutions in a quick check that didn't waste any time on simulating physics or collisions. In this check, I recorded the max rotational speeds the arms reached. Finally, I adjusted the period for each robot to ensure the fastest arm of every robot would reach the same max speed. This allows more efficient solutions to run at faster rates and get more cycles in during the simulation, while also making sure that individual sine waves within a single solution all sync up perfectly. Within the first few generations, we can see the massive improvement this change has on the algorithm. The new guarantee of an arm hitting max speed during the cycle, and the new consistency of highly repetitive solutions made a big difference. The last big change I made was to get rid of any solutions that didn't hit the ground. This was easy to check, since we're already evaluating the arm speed when setting the period. In the initial check, I recorded if any of the arms ever reached an angle low enough to hit the ground, and if they didn't, they were replaced with a solution that did. I thought this change would have a larger impact on how the algorithm played out, but when I first ran it, it seemed to be doing worse somehow. Eventually it caught up and even surpassed the last algorithm, but overall, this addition of ensuring an arm would hit the ground didn't seem to have a large effect. That's enough technical stuff though. Let's check out some of the best and most interesting solutions the algorithm came up with, played out on the actual robot. But before we get to that, let me thank this video's sponsor, PCBWay. PCBWay offers custom services around PCBs, CNC machining, and 3D printing. I'm looking forward to using their CNC and 3D printing services in the future of this project. The large number of materials and manufacturing processes they offer open up many possibilities for future designs of the robot. Their website has a ton of great information explaining all of their capabilities, so if you need any custom parts or PCBs, check out their link in the description below. I think this was the most interesting solution the algorithm was able to find. It's a movement where 5 of the arms hit the ground, making the bot take one slow, large step at a time. The fastest one is this, that uses 3 of its arms to walk. Even though the steps this one takes are smaller than the last, they are much more efficient, with parts of the base moving during most of each cycle. Here's one that uses 2 of its arms to move. The fitness function thought it was traveling really far, but that's only because the simulation only lasted for 10 seconds. If it had been longer, it would have seen that the robot was just pivoting around in circles. To get it moving in a straight line, I modified it to mirror the movement across the center line every other cycle. This causes the top plate to snap to the mirrored position between cycles, and probably breaks the speed limit I had varied the period to meet. But it doesn't seem to hurt anything, so I'll go with it. After seeing this, I wanted to see how mirroring across the center would affect the first movement. It moves relatively straight on its own, but still does rotate some, twisting a bit after a few steps. Mirroring the side straightens that out, but I noticed there's still a lot of time wasted in the movement setting up the next step. So I started testing what would happen if I removed that portion of the movement, where the arms are all floating above the ground. Eventually, I cut it down to just the portion from where the arms first hit the ground to where the base settles back down. With this working, I decided to try and speed it up to see how fast it could go. At 2 times speed, it worked pretty well. But at 3 times speed, it just sort of stayed in place. I think the biggest limit on the robot's walking is the size of its base. There's only a small angle between where the arms hit the ground and their max travel. Additionally, all the dimensions of the arms, top plate, and base were never optimized for walking. I think it would be interesting to represent some of these dimensions in the genotypes and try to evolve the shape of the robot alongside its walking movement. It would be cool to see what a robot that evolved its shape and dimensions alongside its pattern of movement would look like. Also, I would like to see how different ways of defining movements could work. Having a sine wave for each degree of freedom, all with a constant period, is a pretty big limit on the range of solutions available. Lastly, the methods that I put in place after solutions had been found, like mirroring movement across the center line or trimming off sections of the cycle, could have been toggled on or varied within the genotypes and evolved during the process instead of being added on afterwards. Using a genetic algorithm on this problem has been a lot of fun. I find it so cool that it shifts the problem away from looking for a solution directly, and places the focus on finding a way to represent a solution. I mentioned some alternative ways of representing solutions, such as getting away from the combination of sine waves, adding genes to change physical dimensions, or adding genes to cut out portions of the movement. I'm sure there's many far better ways to define solutions, so if you have any ideas, I'd love to hear them in the comments. Thanks for watching.